You who are attending class today are the lucky ones because you get to hear about the most important probability distribution in modern history, the Gaussian distribution, okay? So today we're going to talk about the Gaussian random variable. Which is, as I said, probably the most important random variable that you're going to need in your engineering career, okay? And this is probably already semi-familiar to you as the kind of famous bell curve, right? So what it looks like, before I give you all the gory mathematical details, is basically it's symmetric around a middle value, mu, or the mean, and it looks kind of like a nice symmetric hump. It doesn't go up like this at the end. And this is kind of like the general sketch of what it looks like. The formula for it is, I'll give my little f some tail here. So it's 1 over square root of 2 pi sigma. The sigma is not under the square root. E to the minus x minus mu squared over 2 sigma squared. And so just in terms of terminology, mu is the mean, what we call the mean. Sigma is what we call the standard deviation. And we already, I guess I'm already at the bottom of my page here. We already kind of introduced this word, but you know, sigma squared. Oh, I'm at the bottom of the page. How can I do this? Sigma squared is called the variance. Okay. And so, you know, normally for a random variable, I would actually go through the trouble of proving this is the mean, this is the standard deviation, this is the variance. But in this case, as it turns out, we can plug the mean and the standard deviation right into the formula for the PDF, so it kind of gives us some direct control over the behavior and the shape of this function, okay? So this is, you know, again, you hear it called the bell curve or the bell-shaped curve. It is often also called the normal distribution, which is probably the most common name for it. And it comes up all the time. It's observed all the time as modeling real-world phenomena, such as, for example, you know, population statistics. So if you were to take all the students at RPI and you were to graph their heights, for example, they would probably follow a curve like this that's centered around whatever it is, you know, 5'8", and there would be some people who are super tall and some people who are super short, but most of them would be kind of packed around this central value, okay? Test scores, generally, you know, there's some people who ace the test, some people who bomb the test, and a bunch of people who are just kind of like clustered around the mean. In the electrical engineering world, you know, things like communication noise. So if you're taking a higher level course and we're talking about, you know, what I transmit over the channel versus what is received over the channel, usually the received signal is corrupted by some sort of a noise, right? Could be thermal noise, could be noise that comes from cables being too close together, and often this is well modeled as a Gaussian distribution. Measurement errors also are typically Gaussian, right? Meaning that if I had a physical sensor that was measuring some value, and even though the value was constant, I would plot what the sensor reads, and it would be, you know, kind of up and down around that middle value. But the up and down, you know, the model of the noise is usually Gaussian, okay? And furthermore, you know, as I'm going to talk about, I guess I'll preview it in a couple of pages, but one of the reasons it's called the normal distribution is because, you know, it turns out that no matter what my underlying random variable is, no matter what my model is, if I add a bunch of those random variables together, over time, what will happen is that the distribution will kind of converge to this Gaussian distribution, which is really useful because it means that no matter how weird our noise, how weird our probability model might be, if I add a bunch of those independent variables together, eventually I get things that look very much like Gaussians, right? So in some sense, things in the limit become Gaussian the more I add them up, okay? And so the idea is, the intuition is that, you know, there's a high probability that I'm close to the mean and a lower probability that I'm out at the edges, right? And the tightness of the distribution is controlled by this parameter sigma, right? So if I have a small sigma, that generally means that things are very close to the mean. So if I were to plot my distribution, it might look something like this, right? Super, I mean, it doesn't go below the axis, that's poor drawing, right? But super peaked around the mean, right? Whereas a big sigma is a little bit more spread out, maybe something like this. Now remember, no matter what the sigma is, the integral under this curve, the total amount of probability has to equal 1, right? So if I've got a sharp, spiky distribution, the PDF will be higher in the middle in terms of absolute value than it would be for a big sigma distribution, okay? Now there was a question on the last homework. I guess I maybe used a term that not everyone was kind of like on board with yet, which is kind of like probability mass, right? Probability mass just means kind of how much there is under the curve. And so I know that if I'm looking at the whole curve, I have a mass of 1 unit, right? Because I know probabilities have to integrate or add up to 1. And then kind of, you know, I may use in a slangy way saying, okay, what's the probability half the mass is on this side of the line? You know, that's kind of like just how much of the area under the curve is under this side of the line, right? So, okay. So it may not be obvious, I mean, it's certainly not obvious, like why this equation necessarily leads to a valid PDF, right? How do I know that this thing integrates to 1? Clearly, it's positive, right? Because this is e to the minus some, you know, positive number, and so there's nothing in this formula that can go negative. The only thing I have to figure out is why is it true that it integrates to 1, right? So just for laughs, let's just prove why that's true. This is something that, again, is like a little bit of a mathematical trick, so it's more just like having fun with math than it is, you know, something that you really deeply know. But let me just prove it for you in case you're wondering why it's true. So proof that this thing integrates to 1. Well, I have to integrate from minus infinity to infinity this PDF dx. And one thing to remember is that, you know, when I show you this picture, every value on the x-axis has a possibility of occurring, right? The Gaussian never goes all the way to 0 anywhere, right? So even for a very sharply peaked Gaussian, say that this mean is at, you know, 0, there's still some infinitesimally small positive probability of things occurring way out in the range of like 10,000 and 100,000, right? It's super, super duper unlikely to happen, but every value on this x-axis has some non-zero value of the PDF, which means that I can't get away with just kind of simplifying this integral to some positive range. I've got to do the integral from minus infinity to infinity. And so let me plug in what my equation is. It's 1 over square root of 2 pi sigma e to the minus x minus mu squared over 2 sigma squared dx. You don't really have to worry about writing this down in gory detail if you're not like, it's not like on the critical path, but, you know, just for exercise it might be good. So first thing I'm going to do is I'm going to do a change of variables, basically saying that, okay, you know, what I'm going to, you know, what used to be called x minus mu, I'm going to call x. That doesn't really make any difference in the integral. It's just like saying, okay, I'm going to shift everything so this peak is centered around 0, right? So that means I kind of get rid of the mu part. So that means I have e to the minus x squared over 2 sigma squared dx. Now I am going to get rid of the sigma by another change of variables, basically saying that, okay, I'm going to change from x to x over sigma, right? So that means that my dx prime is 1 over sigma dx. So that means that I already have the 1 over sigma dx over here, and my integral is going to become minus infinity to infinity, 1 over square root of 2 pi e to the minus x squared over 2 dx, right? I got rid of the sigma. Now, here you're still stuck, right? Because this is not something that you can apply any tools from calculus to simplify, right? You never encountered this in your calculus class. So here's the trick, which I'm going to do. I'm just going to call this k. I'm going to hope that this k is equal to 1, but I'm just going to give it a name for the moment. And now what I'm going to do is I'm going to say, well, what if I were to consider k squared? Okay, so I'm going to do a kind of a devious thing of proving that k squared is equal to 1, which is then the same thing as showing that k is equal to 1. So k squared means that I'm just going to, you know, have two of these integrals put together. And since they're in different variables, I need to have different, you know, names for these variables. So I'm going to call one x and one y. And then I'm going to collect all this stuff together into a double integral, which is kind of like, seems like overkill, but all right, let's do that. Seems like I'm making things worse instead of making them better. But here's the other kind of mathematical trick, which is to say, okay, you know, x squared plus y squared, this should kind of ring a bell that this is kind of like a polar thing, right? This kind of looks like polar notation. So what I could do is I could say, okay, I'm going to let that means that x squared plus y squared is equal to r squared, and my dx dy becomes an r dr d theta. Then in polar coordinates, this integral becomes my theta goes from 0 to 2 pi, my r goes from 0 to infinity, and then I have e to the minus 1/2 r squared. The dx dy becomes an r dr d theta, r dr r. So now I can say, okay, well, there's no thetas in here, so if I just integrate the d theta part out, that's going to give me a 2 pi, and that's going to cancel this 2 pi. So now I've got something that is just in r. And now life is good because I've got the derivative of that r squared now sitting in my integral. I didn't have that before. That's what made it difficult. Now I can say, okay, this looks like minus e to the minus 1/2 r squared evaluated at r equals infinity, r equals 0, right? Because this is like saying that if I took the derivative of this, what would I have? I'd have a 2r times a 1/2 coming out, or I have a negative 2r times a 1/2 coming out. That would produce this r here. And so now r equals infinity gives me e to the minus infinity, which is 0. R equals 0 gives me minus e to the 0, which is minus 1, which gives you 1. So what I figured out was that k squared equals 1, and that tells me that k equals 1 itself, which means that I proved what I wanted to do, right? So again, this is just like, you know, math on a rainy day, you know, just for fun, showing that you can do, you know, changes of variables and so on. You know, I'm sitting in my office all day. I don't really get to do a lot of math, you know, like this anymore, so I take the opportunity when I see it. Okay, so we showed this as a real PDF, okay, that's nice. And let me just say on paper, so that you know what's coming in a month or so, the preview of why we think the Gaussian is so important is what's called the central limit theorem. This is one of the key theorems of probability. So here's the theorem, and I'm not going to worry about proving anything right now. What I'm going to say is if I have a bunch of random variables, so if these are independent random variables, and I realize that I haven't really given you all the machinery to understand this yet, but this concept we'll come back to. I just want to give you a little preview. So what I'm saying here is that suppose I have, you know, some distribution, right? Doesn't have to be Gaussian, could be anything, could be uniform, could be binomial, could be whatever, right? No matter what random variable I choose, as long as I keep on drawing observations of that random variable and add them up, right? So basically, the key idea, which is kind of cool, is that the kind of average of these variables as I add more and more of them up, turns into a Gaussian distribution in the limit. Right? So that's kind of a good result for us because it means that, in electrical engineering, for example, a lot of times we're adding up lots and lots of the same type of noise, right? I'm transmitting a signal over the channel, and the channel's kind of got this, so-called white noise, which means that, every time the noise gets added, it's independent of any other noise, and it's the same distribution as I had before. That means that, life becomes Gaussian if you just add up enough stuff. And actually, if you remember when we did the binomial random variable long ago, we had the Plinko board, right? And we did that little computer demonstration showing that as I drop more and more, Plinko dots down the tree, eventually that distribution started to look like this bell curve, right? And that's exactly what the central limit theorem is saying, is that maybe when I only have 3 coins, that bar graph doesn't look very much like a Gaussian. But when I have 1,000 coins, I step back and look at it and say, oh, actually, this looks like a pretty good Gaussian. Right? We'll talk about this more and even talk about how to prove it, once I've given you about a month more probabilistic machinery, right? But I kind of want to give some intuition as to why we care so much about talking about the Gaussian in the first place, okay? So let me pause and ask, any questions or comments? All right, so I told you about the PDF of the Gaussian, right? So the natural next question is, what is the CDF of the Gaussian, right? The cumulative density function. So let's remind ourselves what that means. So what is the CDF for the Gaussian random variable? Well, let's remember our definition. This is capital F. This is the probability that I'm less than a certain value, which is like integrating from minus infinity up to that value of the PDF. Maybe I should give this a different name, like f of y dy. Let's substitute in what is our integral here. This is like saying, 1 over square root of 2 pi sigma e to the minus y minus mu squared 2 sigma squared dy. And just for the same reasons that I had a hard time doing this before, this is unfortunately the best I can do. This is where I have to stop because there is no closed form answer to this integral, right? Again, this came up, I think, again, in some conversation. What does it mean closed form? Closed form means that I can actually, carry out this integral and come up with a direct function of x. Here, I'm kind of stuck, right? This integral is not something that you'll ever be able to do by hand, and so now that means that you have to do it numerically, right? So remember back in the day, calculus 1, how did you compute, or how did we define integrals in the first place? Remember that there was this thing called Riemann sums, right, where you had to say, okay, here's my Gaussian distribution. What I could try to do to approximate, the probability that I was less than this value is I could chop this thing up into a whole bunch of tiny rectangles like this. This is actually just the definition of what integration is, right? And so on. So, this is how, if you ask MATLAB to do a numerical integral, this is how it does it, right? Is basically by chopping up your interval into a bunch of little pieces and then adding up the sum of a bunch of these rectangles. And we know that the skinnier these rectangles are, the closer my sum of rectangles gets to the actual area under the curve, right? So, what that means is that in practice, we need to use tables of numbers or computers to be able to give us the values of the CDF, right? And actually that comes back to a question like, what was asked earlier, well, can't we just, aren't the PDF and the CDF kind of equivalent ways of thinking about the same distribution, so why couldn't we just do everything with the CDF? Well, that's possible, except for example here, the super important Gaussian random variable, I can only give you the PDF, I can't even define the CDF, right? So the CDF is not a useful quantity, whereas the PDF is, right? So what that means is, I kind of know intuitively what this looks like, right? So I can think about what it should look like. I can say, okay, well, I know that the distribution is symmetric, right? So at the value mu, I have to have accumulated exactly 1/2 of the probability, and it has to start at 0, it has to climb up to 1. Now, if the sigma is small, right, kind of referring back to this picture, if I think about my CDF as I'm moving my hand along here, so I'm going to have 0, 0, 0 for a long time, and then I'm going to have a sudden spike up in accumulating probability, and then I'm going to, get almost all the way to 1, and then I'm going to kind of taper off again very quickly. So for a small sigma, this looks something like, this, right? It goes up really fast. And for a big sigma, it may take me longer to get up to a half, and it may, kind of be a smoother looking curve. So maybe it looks like, something like this, flatter for big sigma. Okay. Now, it would be really cumbersome to have to produce this numerical table for every possible value of mu and sigma, right? That would be a real pain. And so what happens instead is that we only make one lookup table, right? And we call it the standard Gaussian, okay? So the idea is that, let me just write down, so we must do numerical integration or refer to a table to actually compute CDF values. And so we do this with reference to kind of one canonical Gaussian, which we call the standard normal. Which basically is saying that the mean is 0 and the standard deviation is 1, right? That means that I have a particularly nice form for the CDF, right? This basically says I integrate, since sigma is 1, that drops away. I integrate from minus infinity to x, e to the minus y squared over 2 dy, right? This is the corresponding CDF. And so people make tables of these values, right? And that's, for better or for worse, exactly what you're doing on this homework and what I'll ask you to do eventually when we look at the exam. So again, just kind of sketching out what that means that for a nicely shaped bell curve that's centered around 0, I have a table that gives me this number, phi of x, for any x that I ask about, okay? Now, in practice, you actually typically, and the way that our book does it, and the way I like to do it in class, is typically, instead of giving you actually this value, we actually instead look at a table of this value, which is like the tail of the Gaussian after x. And that we give a name of q. This is like the tail of the Gaussian. Okay? And so here's an example, which I'm going to use as we go throughout class. Here's an example of the Q table for a standard Gaussian, which is probably a little bit too small to read. Not that it's really important where the numbers are, but basically it starts off saying when I'm at 0, right, then I've accumulated, there's half of the distribution left. So the top value is 0.5. As x gets bigger, then this number gets smaller and smaller and smaller. So this is basically saying that, when I am 10 away from the mean, I've got this super duper low value of the probability of being in the tail, okay? And so for those of you that have ever done any sort of like statistics, you may remember some sort of rules of thumb, for example, that says that if I'm plus or minus 3 sigma on either side of the mean, that accounts for most of the probability. And here I can be concrete about that. This is basically saying that, for example, you know, when, so here, you know, I guess this is in terms of z instead of x. So basically saying when z equals 3, then q of z is 1.35 e to the minus 3, which means it's 0.001, right? More or less. Did I get that right? Yeah. For some reason I had like momentary lapse of worry, right? So this is basically saying that, you know, if I have a, you know, the stuff that's out here is, you know, less than 1% of what's left in the Gaussian. So typically, you know, when I look for, you know, stuff that's beyond 3 standard deviations from the mean, things are super unlikely, right? And 2 standard deviations from the mean is also already pretty unlikely, right? So 2, if I look up this, I say q of 2, this is equal to 0.02275, right? So only 2% of the mass is beyond 2 standard deviations. And in fact, you know, if I looked at kind of this on both sides, I could say, okay, if I also consider what was on the other side, so kind of 2 standard deviations plus or minus, then there's like 4% of the stuff left out there, right? So, you know, it's kind of handy rules of thumb, okay? So what we're going to do today is a whole bunch of examples using this table so that you know how to use the Q function for these kinds of computations, okay? So just as a side note, it is true that you could use the computer to do this kind of thing, right? So for example, just for your, you know, future knowledge, it's definitely true that you can do this in MATLAB. So this Q value is related to what in MATLAB is called ERF, E-R-F function, or actually it's called the error function. But it's not exactly the same, so you got to be careful. So if you want to know how they're related, for future reference, they're related in this way. So you have to do a little bit of, you know, footwork to get from what MATLAB gives you to Q of x. Now, it may be true that actually there may be a more direct way to do it now in MATLAB, but this is the way it used to be. And if you go to Wolfram Alpha, so let me just go here. I think that Wolfram Alpha is a great way to check your work when you're doing these kinds of things, but also keep in mind that you're not going to have Wolfram Alpha on the exam. So if you just type, luckily, Q of 1 into Wolfram Alpha, it knows what you're talking about, and it gives you a value, you know, 0.158, which I can compare to my table, and I see it's the same thing, right? So definitely, you know, it's okay if you're sure that you know how to use the table. It's okay to use this kind of thing on the homework to just plug in values and get numbers, but keep in mind that you're going to have to know how to use the table for the exam. And that's all I'm going to do today. Question or just stretching? Okay. Okay. Other questions or comments? All right, so I'm going to do a whole bunch of examples, more or less, for the rest of class. I guess actually before I forget, the last thing I wanted to kind of mention in case you were ever wondering is that, so you may have heard in kind of business speak, the world of like Six Sigma, right, is like this big business certification thing. And so that is kind of related to this idea of how much stuff is in the tail of the distribution. So just kind of like a side note, this idea of kind of Six Sigma comes from kind of like, well, I guess the way it's actually defined is, and if you're a business major, don't come after me for how inaccurate this may be. My understanding is basically, the idea is you look at the Gaussian distribution and you want, you know, this tail value to be vanishingly small, right? And so I think that the rule of thumb is that you have 3, you know, errors or 3, you know, mistakes in a million is kind of like the Six Sigma philosophy. Like if you're making parts in a factory, you know, that's like the standard of quality that your factory can tolerate, and then you're Six Sigma certified, right? Now, when I was preparing for class, I was trying to figure out, okay, so why is that follow from this table? Because I look up Six Sigma, and Six Sigma is like much, much less than 3 mistakes in a million. So I was trying to figure out what the deal was. So for some reason, there is an adjustment to Six Sigma that comes from, I guess the idea is that saying, okay, if you're 6 sigma away from the mean, already this is vanishingly small. This is like 9 e to the minus 10th. But if your manufacturing process went off somehow and you were 1.5 standard deviations away from the mean, then if you add it, there's some sort of like, adjustment by 1.5 standard deviations. This is the 3 errors in a million, right? This is the 3 e to the minus 6 that this comes from. I guess it's like saying that if in the future your machine or your process was corrupted so that instead of being where you thought you were at the mean, you were actually 1.5 standard deviations off, you'd still be 3 errors in a million, right? So it's kind of like, future-proofing your manufacturing process, right? So in the beginning, 6 sigma is very unlikely, but even if you're drifting by 1.5 sigma, that's where the 3 errors in a million comes from. This seems like something that a non-engineer came up with, to be honest, but that's where it comes from, so you can impress your friends. Okay, so let's do some examples. And it's really important, I think, to understand, like, for me, solving these kinds of problems kind of comes down to thinking about how many standard deviations away from the mean am I, right? That's a different way of phrasing the idea that I have a 0 mean unit standard deviation random variable, right? So, so to use these tables, so to use the Q function tables, we need to convert whatever Gaussian we have to this standard normal, meaning mu equals 0, sigma equals 1. And so let's suppose that I'm asking a question like, probability that, so this is like the CDF of some Gaussian, could be any Gaussian. The idea is, what I can do is I can subtract mu and divide by sigma, and actually, I'm going to make I know people complain about this, I'm going to make a z on this side just to kind of make this a little bit less confusing with all the x's. Now I've got this weird. This is basically saying, okay, what I'm going to do is I'm just going to subtract mu and divide by sigma on both sides of this equation. Now this thing is basically a standard normal random variable. Which means I can use my table. So I'm going to maybe call that like x tilde, for example. So let's do a little bit of practical examples because I know this is a little bit abstract, right? So let's use this. So let's suppose that x is a Gaussian random variable with mean 5 and standard deviation 2. Okay? What is the probability that x is greater than 8? Okay? So what do I want? I've got a picture that looks like this, where the mean is 5, and I want to know what's the probability that I'm greater than 8. Okay? Well, I want to turn this into an equivalent question about my standard normal, right? And so an equivalent thing is to say, okay, equivalent question, what is the probability that y is greater than, 8 minus mu over sigma, where y is the standard normal, right? The probability that y, if I simplify this right-hand side, is greater than 1.5. Right? So kind of I'm converting in the world of x to the world of y, where I'm at 0 mean, and this number is 1.5. These things are kind of like equivalent statements. And again, the way I like to think about this in words is basically saying, you know, how many standard deviations away from the mean is 8, right? So it's, you know, I'm 3 units away from 5, and that's 1.5 times 2, right? So that kind of tells me that 1.5 is the number I should be looking for in my table. And then I look at my table, and I say, okay, I look up 1.5, and I see that this is equal to 0.0668, okay? And that's all it is. Or let's suppose I wanted to say, okay, what's the probability? Let's try a different way. So how about same random variable? What's the probability that x is in the range 3 to 6? Okay. So remember, my mean is 5, and I want to know what's the probability that I am in. That was like a crappy picture. I'm going to dignify that with continuing. Okay. First, I should draw this. Then I'm going to say, here's 5, here's 6, here's 3. And I want to know what's the probability that I'm inside this region here. Okay. Well, this is a little bit less straightforward. But I can kind of reason about this and say, okay, well, clearly this is the same thing as 1 minus the probability that I am above 6 minus the probability that I am below 3, right? Those two things kind of are easier to compute and come from the Q table, right? So here, this is like saying, okay, well, this, how many standard deviations away from 5 am I? So I have to remember my standard deviation was 2 originally. So here, this guy is like Q of 1/2. And this guy is like Q of 1, right? Because if I were to flip it around and say, okay, you know, this is where, you know, when you're on the negative side of the mean, you have to think about, okay, it's true that Q of 1, if I were to look it up, is really talking about the probability that I would be greater than 7, but this thing is symmetric, right? So, you know, I'm kind of looking on the other side. So I can say, okay, I've got 1 minus Q of 1/2, which is whatever, minus Q of 1. I look at my table, which I lost. Okay, so I got 1 minus Q of 1/2 is 0.3085. Q of 1 is 0.1587. And I would do that math, and I would end up with whatever, 0 point something, 532, more or less. Okay. Is that right? For some reason, I feel like that's somehow wrong, but that's what my paper says. So one thing that we can do, let's just go for a second to Wolfram Alpha to do our sanity check. Right, so I have the same, so you're going to have a problem though with, I think if you combine a bunch of Q functions here, you may have an issue in Wolfram Alpha. Oops, well, partially because I put an equal sign there. Does it know what I'm talking about? No. So here, you would have to actually compute these things individually. and then subtract them manually unless I'm missing something, which is a little bit clumsy, right? So I'd say 1 minus 0.3085 minus 0.1587, and I get 0.5328, which I guess is exactly what I said I did. I don't know. For some reason, I was not happy with that answer. Okay, so I was okay. Okay, so let me pause and ask. So questions about this process? So you're going to get a lot of exercise doing this on the homework. Let me do a couple more examples here, which kind of turn it around a little bit, okay? So again, typical probability professor thing is to kind of go in reverse, right? So now I could say something like, okay, let's say that x is a Gaussian random variable with mean 5 and standard deviation 3. Find me a number, find a, such that the probability of x being less than a is 0.9. So that's like saying, okay, I don't know where I'm stopping on the x-axis. I know that I want this number here to be exactly 0.1, okay? And so, again, there's a kind of a mathematical way of cranking through it. Let me just kind of give you the intuitive way first. The intuitive way for me is saying, okay, now I'm looking for a number in this table so that the Q function is 0.1. And I look at this and I say, okay, well, 0.1 is, it's almost this, right? And it's almost that, but it's not quite between. So it's somewhere in between these two values, right? This one is 0.11, this one is 0.096. So this is the point where on the table, I would give you credit for kind of like, guessing some number. It's probably closer to, well, it's hard to know which way it's closer to. So what you could do if you were, again, doing this with Wolfram Alpha is you could make some guesses and say, okay, I think this number is somewhere between 1.2 and 1.3. If I try like 1.25, I see it's 0. It's not quite yet. There's still some stuff to go. How about 1.27? I'm getting better. How about 1.29? Now I've gone too far. So 1.28, right? And here this is, fine, right? Again, I'm not going to penalize you for like being a few decimal points off in your guess, especially if you're using the table, right? So in an exam situation, you could look at this and just eyeball it and say, I'm going to put it somewhere between these two and compute the number, and as long as it's roughly right, you should be fine, right? When you're doing the homework, you can screw around with Wolfram Alpha a little bit if you want it to be a little bit more precise. So in this case, we did do this screwing around, and we found out that the corresponding z equals 1.28. That led to the tail of the distribution being basically what we wanted. And now this means that I should be about 1.28 standard. Oh, I'm sorry. Everyone's pointing at me, looking disappointed. Right? So what I was saying was that I found out that if I had a z value of 1.28, that the corresponding number in this table would be exactly that 1/10 that I'm looking for. So that tells me I need to be 1.28 standard deviations away from 5. So my answer for A is 5 plus 1.28 times 3 standard deviations, which is 8.84. So questions about this? Let me do another one along this line. This is, again, kind of similar deal. So how about, again, let's stick with this Gaussian over here, continuing the idea, find me a value of b greater than 7, such that the probability of x being in the range 7 to b is equal to 0.2. So I think it always is helpful to draw the picture, right? So here I'm saying same Gaussian, 7 is at one end, B is at the other end, and I want to know what's the probability, what is B so that the area under the curve there is 0.2, okay? Well, I can start off by saying that this area has to be, you know, the full area of 7 minus just the part that involves B, right? So this part I can compute. This is going to be Q of 7 here is basically 2 away from 5, so it's 2/3 of a standard deviation, right? And then this number is going to be basically Q of B minus 5 over 3. That's basically however many standard deviations B is away from things. And I want this to be equal to 0.2. So now I have to look up my Q of 2/3. Again, I look at my table and I say, well, Q of 2/3 is going to be basically somewhere between 0.6 and 0.7. I know it's going to be, I want to know what Q of 0.66 is, right? If I want to, I could go back to Wolfram Alpha and do a quick check. Q of 2/3 is 0.252. So that means I've got, this is like 0.252 minus the thing I don't know. That has to equal 0.2. So now I can kind of go back and say, okay, that means that I'm looking for B so that Q of B minus 5 over 3 is equal to the leftover part, 0.052. And now I have to go back to my table and say, okay, so what value of B has this 0.052? That is going to be somewhere like between here and here, right? This is 0.0054. This is 0.044. It's going to be pretty close to 1.6. So I'm going to guess, you know, let's guess, you know, 1.6, you know, 2, let's say. And then that would mean that my B minus 5 over 3 would be equal to 1.62. So my B would equal to 5 plus 3 times 1.62, which would be whatever it is, 9.3, 1.62 times 3, 6, 8, 4, 9.86, okay? So that's the basic idea, and you're going to be going through this a few times, seesawing back and forth in the homework of either computing probabilities directly or computing values that are kind of more like on the x-axis, given that I want to have certain areas under the curve. And again, just a couple things to remember is that just in terms of like symmetries, right? So remember that, you know, this is defined as Q of x, but you're only going to find positive values in the Q table, right? So here, this Q table starts at 0 and says that there's half of the distribution left in that tail, right? So this is Q of x. If I'm thinking about, you know, what if I had negative x, right? So that would be like saying how much is left here, right? So Q of minus x, if I'm trying to find it in the table, is basically going to be, well, it's going to be 1/2 here plus 1 minus this part, which is Q of x. So it's like, well, that's what it is, right? It's like 3.5 minus Q of x. It seems like a kind of a weird thing to say. Is that right? Q of negative x is, yeah, I feel like that's okay. The main thing is just kind of like sanity check of which side of the axis am I on. So like I said, you just want to make sure that you're talking about, am I talking about the, no, this isn't right. Hold on a second. So this area here is q of x. So it should be 1 minus q of x, right? Yeah. Okay, sorry, I was like, this didn't seem right at all. So it's basically 1 minus the shaded area. Okay. So in a case like this, where if I had something going back to this, where I'd say, okay, let's suppose I have a Gaussian of mean 4 and standard deviation 2, and I want to know what's the probability that x is less than 1, right? I would draw that picture and I would say, okay, here's 4, here's 1, and I want to know what is this probability. Again, mentally, it's easiest for me to flip this around and say, okay, it's the same thing as being on this side, right? So I could say being less than 3 is the same as being greater than 3. So I'd say something like this is, again, q of 1.5 is how I'd look this up. Even though if you start with this, you'd be saying, okay, I'm looking for 1 minus q of negative 1.5, and I see there's no negative numbers in my table, right? I just have to know how to convert that to the right positive number. So I think that, again, every time you have this problem, just start with drawing a picture, and I think that will kind of help you understand what should be happening. Okay, so one more thing I want to say to close out the day. So let me pause and ask questions or comments about Gaussian stuff. Okay, so last thing I want to say, and I'm not going to belabor this point right now, but we ended up talking, when I first introduced probability mass functions, PMFs, the next thing that we did was to say, okay, what if we had a conditional PMF, right? To say, okay, what's the probability that I had 4 arrivals, given that I know I had exactly at least 2 arrivals, something where you have a changed PDF based on a condition. So the kind of little extra part of today's lecture is to say that, we can also talk about conditional CDFs and PDFs. For example, I could say something like, I want to know the PDF of x given that x is in some range, okay? So I'm giving you some information, some sort of side information, and that changes the way the PDF should look. So we use the same kind of little bar, right? And the way I read this is kind of like given. So kind of my before picture of my PDF maybe looked like, something like this, right? And now I'm telling you, okay, I'm telling you that you're between A and B, right? So now that is definitely going to change the shape of your PDF, right? Certainly it's true that I can no longer have any probability of being outside of A, right? So it's going to change the overall mass. And so how does that actually work? Let me be really explicit, because typically we kind of get from CDFs to PDFs, right? So if I'm being really proper, this is like basically the derivative of the CDF. What I'm going to have basically is something where I'm normalizing by the probability of being in this region, right? So this number, whatever this is basically the integral from A to B of the PDF. Or a different way of thinking about it is it's the CDF evaluated at B minus the CDF evaluated at A, right? It's basically how much has accumulated between A and B. And so if I'm going to normalize this, the result should be basically 0 if x is less than A, and 1 if x is greater than B, because I've confined myself to that region. And in the middle, it should just be kind of like the normalized probability like this. Right? This is just saying this is the, this thing here is just the probability oh, wait a second, this is the PDF, right? So it's 0 actually outside here. It's like this. This is the PDF, not the CDF. So this is basically the PDF that I'm in this range in the first place. Right? So it's kind of like saying that, inside here, the integral into the curve is this probability. If I tell you I'm there, then I have to normalize everything so that the probability, again, sums to 1. So all I'm kind of doing is I'm dividing through by the probability of this event. So I think there's a question on the homework that just kind of does this with the Gaussian. To say, so, okay, for example, what's the probability that the Gaussian is beyond 3 standard deviations, given that I told you it's already beyond 2 standard deviations? That's the kind of thing that you should be able to figure out, again, using Q tables. Okay, comments or questions? All right, I think that is pretty much all I have to say today. So, in that case, I will see you on Monday.